having me here, Susan and Andy and others. And as Don said, this is somewhat of a continuation of a talk that started this morning with Gori Ghosh, who outlined an X-ray structure for a splicing kinase with an SR protein bound to it. My talk is going to be focusing largely on mechanistic considerations in these types of reactions, these types of polyphosphorylation reactions. We have a long history of studying single sites where a kinase comes in and modifies a single site. And this was very attractive to our group to look at multi-site because it offers a lot of new constraints on how a kinase could interact with this substrate and modify it. I won't go through too much of this. This is Gori gave a preview on this. But we study the SR proteins, which are essential splicing factors that help to assemble the spliceosome so that the spliceosome can be active and catalyze the necessary trans-esterification reaction. Is this a pointer? Okay, thanks. Excellent. So a number of SNRNPs need to come together to form an active catalytic complex of the spliceosome. In the beginning here, we have to have recognition, and there's scant nucleotides around there for recognition, but there's a multitude of proteins within the spliceosome that help out in this. One class, or family of proteins are the SR proteins that are essential. They're important, we know, in exon definition, 3', 5', but they also play roles in other events during the spliceosome development. But these are essential splicing factors. They have the general domain organization shown here, where they'll have 1 or 2 RNA binding motifs, RRMs. Not surprisingly, these things bind to the pre-mRNA at these exonic splicing enhancer sequences, and they can guide other aspects, other components of the spliceosome to the splice sites. Why we're interested in them is that they have these C termini here that can be anywhere between 50 to 300 residues that are very rich in arginine, serine, and repeats. And these things become phosphorylated. I'll be talking about ASF. We learned a lot about its structure this morning. But that's a 50 residue C terminus here, very rich in serine. And many of these serines are flanked by arginines. They have arginine, serine repeats. And we know quite well that these RS domains are polyphosphorylated in vivo. We know that, at least in vitro splicing assays, that these RS domains are important both in distributive and alternative splicing for some substrates, not for all. We also know that phosphorylation is critical in splicing, but that hypo or hyperphosphorylation, that is too much or too little phosphorylation, can actually inhibit splicing. There's a lot of investigation now into the role of these RS domains in splicing. It has been shown that phosphorylation of these can actually control splicing of certain pre-mRNAs, such as the caspase genes. But there have been other studies showing that the RS domains are surprisingly not so important in cell viability. So there's lots of questions regarding these RS domains and their involvement within the spliceosome. What we know quite well is that phosphorylation and polyphosphorylation, to be exact, is important in localizing these factors for splicing. So they indirectly at least have a role that way. There's this cytoplasmic kinase that Gori talked about, SRPK1. There's SRPK1 and 2. It's not exclusively in the cytoplasm. You can see some in the nucleus, but it's largely in the cytoplasm. It phosphorylates these SR proteins that have these RS domains, and that's sufficient to link it up with a transportin that gets it into the nucleus, and they can stay in speckles until they're acted upon by a secondary kinase, of which Clixi is the prototype, that does some further phosphorylation, gets it out of these speckles where they can link up with the spliceosome and aid in splicing. I should say that while phosphorylation is critical in establishing the boundaries of the exon where we're going to splice, dephosphorylation is also important in getting an active spliceosome. And dephosphorylation may also be important in getting the RNA out. So these kinases are involved somewhat in a cycle here for these SR proteins. So our lab is interested in the mechanistic enzymology of these kinases. It presents an interesting problem to us because all of these serines that get phosphorylated are right next to each other, almost right next to each other in large series repeats. So the question is, how do you put these phosphates on in such close proximity? And Gory's structure is giving us a lot of insights into that. Questions that we're going to briefly go over today is this idea, the mechanism in which they get attached, whether put on processively or in a distributive manner, whether the attachment is a regio-specific one or a residue-specific one, and also whether there's an order to how it's put on, is it directional or random. This idea of the mechanism we addressed early on, and we wanted to address whether it was a distributive or processive mechanism. Now, a distributive mechanism is in which the kinase would come in and put phosphates on, release, come in, sort of a hit and release mechanism, and it would continually do this throughout the RS domain. But we also wanted to entertain the possibility that it could be processive at some points in which it would just stay latched on and put the phosphates on and kind of slide along the RS domain. To address this, we took advantage of some methodology that's very old that's been used for DNA polymerase, and that's a start trap experiment. And basically what we're going to do is we're going to try to trap out any type of intermediates, because if you have an extraordinarily distributive mechanism, it would be kicking out intermediates that you could isolate and collect in some way. But if you had a processive mechanism, you couldn't do that. And the method we used originally was a peptide-based one, but we eventually started using these inactive forms of the kinase of SRPK1 that's very capable of binding the RS domain, but of course is inactive. And then what we wanted to do is see whether this could trap out early intermediates or whether it was ineffective at controlling the reaction, which would be indicative of processive type mechanism. And what we found out was that this inactive kinase could slow the reaction down, but only after about 8 steps happen. This is a typical type of reaction you'll see with this SR protein. You have this rapid phase over in about a minute or two, and then a slower phase where about 3 additional sites are put on. So this suggested that this kinase would work in a processive manner over some sites and then in a distributive manner over other sites. And this just shows that the trap was actually is thermodynamically functioning. We've also shown that it's kinetically functioning as well. So we're dealing with a kinase that is unusual for us in the sense that it doesn't just hit and then move away. A lot of the kinases don't have very high affinity for their substrate, so it's unusual that this thing would stay on its substrate and do a couple of steps. What we've learned later was that the kinase actually has a very high affinity for the substrate. It's, as Gory said, it was in the low nanomolar region, about 50 nanomolar or so, and that's consistent with this idea of the kinase wanting to stick around on this substrate. We've also explored the substrate specificity of this because remember you have these 2 kinases, one nuclear, one cytoplasmic, and it was controlling the localization of the SR proteins. And what we found is that his RS domain is just loaded with these serines, about 20 of them. The nuclear kinase Clicks-Dye is capable of just phosphorylating that whole thing. It doesn't phosphorylate outside of the RS domain, you know that. But the SRPK was actually a little bit more restricted in the number of sites it would put on. Whereas this would put on 20, this would only put on about 14 or 15. We also showed that this would work in a highly cooperative manner where SRPK could put on a whole bunch of sites initially, and then Clicks-Dye could later put on the other group of phosphates. So it raises the question of if we have one kinase that's just totally indiscriminate and just sees any serine and phosphorylates it, what is this other kinase doing? It must be regio-specific in some manner. This was not at all a very easy question to address because you have a rich arginine serine substrate here basically that you're working on, and you can just easily chew it up. But what we were able to do is put lysines at discrete positions and not mess up the phosphorylation reaction, but we could then cleave that with an endoprotease like C. We get fragments, and we could show by MALDI that we can get phosphopeptides here, and just not going into all the details here, we found that we could find isolate about 10 serines that get phosphorylated in this N-terminal region of the RS domain. Okay. Now, we do get 14 to 15 total phosphorylated, so we don't have them all isolated, but that's all that we can see, and you can't prove anything through a negative, so there could be other sites going on, but we don't see them. And there's certainly enough serines in here to add up to the 15. So this sort of mapping study gave us some feel for what's the structure of this, or the functional structure of this RS domain. It's kind of broken up into two segments, an RS1 and an RS2, where it looked like SRPK phosphorylated here, and then click is likely to do these other residues. And it's consistent with biological studies, cell biological studies that we've done, where you do in fact have two functional segments of the RS domain. It's consistent with the idea that SRPK phosphorylates as RS1, and that gets it into the nuclear speckles. And we know this because we can delete out RS2 and it still gets into these speckles. But an RS2 deleted ASF will not get out of the speckles when click is overexpressed in these cells, presumably because click is phosphorylating these other residues and providing this release mechanism. So it allowed us to begin to understand some concepts about regiospecificity in these SR proteins and how they function in the cell. What we were interested in is to learn more about this kinase because we knew it had a processive component to it. And if it had that sort of componentry, it might also be a directional kinase, just in the same way as a DNA polymerase is processive and it works in a direction. So we wanted to know if it went in one specific direction or another. These are experiments that we've done before the X-ray structure, so we weren't quite clear whether it would go in one way or another. Gory's structure seems to suggest it might be going in one way, but at the time we didn't know that. My graduate student, Chen-Ting Ma, designed this footprinting experiment that took advantage of the fact that we can actually take arginines out, put lysines in there, and then separate the RS domain into two halves. And he did that with this ASF molecule. He had to do more mutations in RM2 because there's a whole bunch of lysines in there, and that took him some time. But the idea is that you could cleave this thing after phosphorylation and get an N and C terminal fragment that you could actually look on gel because there are differences in molecular weight, and then figure out where the phosphates are going early on in this overall process. And then by controlling how much ATP you give this, you can have 1 phosphate, 2, 3, 4, all the way up to 15. You can figure out where the phosphates are going. So what he found was that, in general, these phosphates wanted to go into the C terminus before the N terminus, and eventually you'll get a fairly equal distribution depending on the regiospecificity. This is not a KM phenomenon with ATP because we can do this in a pulse chase mode and we get the exact same results. So this is a property of the enzyme, and it's consistent with this idea that it wants to move in one direction across the RS domain like that. The question we wanted to ask, though, is, was this enzyme so regiospecific that it's confined to the N-terminus? Okay? There's been peptide work, library work done to show that it will go after RSs, and it likes them in repeats. Well, we have RSs in the RS2 segment, but they don't appear to get phosphorylated. based at least on this molding. And again, the absence of data doesn't tell us that we aren't getting phosphorylation there. So we wanted to probe this and see whether this kinase could actually build into RS2. So Chen put a cleavage site right in the middle of the RS domain in these two fragments, and he did pulse chase and ATP mutation studies. And what he found was that the kinase preferentially wants to go into the N-terminus, or the RS1 fragment, but eventually will go into the RS2 fragment. So it's not confined as we initially thought, but kinetically they're different because what happens is in the first minute or two, all of the phosphate is going into the RS1 segment. And then after that happens, then it seems like it goes into RS2. Okay? So the kinase is more residue-specific, but it's regio-specific with respect to dynamics. So we were left with this kind of conundrum here, was that we had this kinase that is directional in a residue-specific manner. It wants to go towards the N-terminus, yet we know that it's also directional in a regio-specific manner. It wants to go to RS1 and then go to RS2. So they kind of oppose one another. To get more insights into precisely what's happening with this kinase, we decided we wanted to figure out exactly where the kinase would initiate along the RS domain, because this might give us some insights into this dilemma of the opposing activities that we have. So what Chen did is he made cleavage sites in numerous places within the RS domain, and if he made it out here, it largely goes towards the N-terminus. We knew that. If he made the cleavages inside the RS1 segment, it largely wants to go towards the C-terminus before it goes towards the N-terminus. And it's consistent with the idea that the kinase is initiating somewhere in here. And if you make cleavage here at 222 or 224, you actually get a more random distribution between N and C-terminal phosphates, and that's shown here. All in all, it's consistent with the idea that the kinase is not specific as far as it wants to start at this serine, and it can't start anywhere else, but it likes a region, an initiation box that's right here, or right at the C-terminus of the RS1 segment. And that makes sense because we know it starts in that region and it works in the opposite direction. I should say that this is not very rigid because we can make alanine mutants here, and we basically just push it over to the next side. So it's not a rigid start, it has flexibility in it. So how do we explain what's happening here? Well, we kind of think this kinase is rather gymnastic in what it can do. One of the reasons I'm happy working on this class of kinase and their substrate because they're so interesting. What we found is that the kinase, for some reason, wants to start in the middle of the RS domain, and that's not too well understood. We have an X-ray structure, which I'll show you in a minute, but it could start in other places, but it wants to go in the center. Once it's there, it just rapidly goes, and it goes to the left, C to N terminal. Many of those steps are processive, about 2/3 of them or so. And then once it's done with that, it seems to want to hop over to this RS2 region and do some more. Now, I'm not quite sure. We know that this reaction here in RS1 is physiological. We know that that's a key fast step that has to happen in order to get these SR proteins into the nucleus. Whether that other reaction that's going on here is physiological, we don't know at this point. And this is speculative, but one thing we do know is that SRPK, as I said, is a cytoplasmic enzyme. It can go into the nucleus, but it's mostly in the cytoplasm. It will go into the nucleus during different stages of the cell cycle. Also, if you take that insert out that we were just talking about this morning, it will go directly into the nucleus. We know why that's happening. That's because the SRPK's insert is interacting with some co-chaperones that keep it outside. But what happens too is that these speckles that are shown here get very aggregated. So I don't know if there's a link between this RS2 phosphorylation, but when SRPK gets into the nucleus, it does tend to aggregate these speckles. That's our proteins that are in the speckles, which will inhibit splicing. So it's not quite clear whether this might be a regulatory function or not. But it just goes to show what this kinase is capable of doing. And although there's RS sequences in these RMs, it won't touch them. Only here. So just a few things I wanted to talk about with respect to this initiation mechanism, because this is something of critical importance if you want to understand the specificity of these kinases and how they function with other exon proteins. What is causing this initiation? And this is getting us back to Gory's structure here. As we heard from this morning, Gory solved the structure of SRPK lacking the insert, lacking RRM1 and half of the RS domain. And he was able to show RRM2 interacting here and a docking site for a portion of the RS domain. Now, it's not the whole RS domain. In fact, it's only a little piece, just the N-terminal part of RS1. The other residues we can't see, all right, because they're disordered. And we have all of these contacts here. So we wanted to ask whether those contacts were what forced this thing to go where it is, or where it starts its reaction. So what Chen did was he began to delete the RRMs. He took RRM1 off, or he moved RRM2 off to the C-terminal in hopes of breaking any contacts between the kinase and that RNM. We wanted to keep one of those RNA recognition motifs around so that we could get two fragments that we could easily identify. And what he found was that when you take out the first RNM, this thing is still very directional. It wants to start at the C-terminus and work its way to the N-terminus. But when you take off the second RNM and you swap it to the other side, all of a sudden it didn't have as much preference. This is a log scale, by the way. And there's about a 30-fold reduction in that preference. So the RRM that's flanking this RS domain seems to be important in telling this thing to go to the center of the RS and then work your way back. Right? The next question we wanted to ask is was this docking groove serving any function? Because Gory, you can see this with a part of the RS domain in there, very nice contacts. And that's shown here. So what we did, a graduate student, John Hagopian, made 6 mutations in that pocket to ensure that it can't effectively bind that RS domain. And what we found was that when you knock out the docking site in SRPK, also we lost this initiation factor. It became a more randomized kinase by the same amount, about 30-fold. Now we've done other things because now we have a mutant kinase, we have mutant forms of the substrate, so we mixed and matched a lot of this. Interesting things that we found is that for a kinase that didn't have an RRM1, and the RRM2 is removed by swapping it to the other side of the protein, was actually not C-terminal preference, but actually showed a small preference for going to the N-terminus. When the docking site was knocked out. I know this is all confusing, but what I tried to do here is summarize a lot of this data. So what we're doing here is we're looking at the addition of various contacts, whether it be the docking groove in the kinase or the addition of RM1 and RM2 and its contacts on the effects of this C-terminal preference, this desire for the kinase to go towards the C-terminus of RS1. And what we found is that if we don't have a docking group and if we don't have these RMs, it actually has the site preference for going to the N-terminus. We can put RMs in and start to get some preference for C-terminus, as shown there. If we don't have any RMs and we just have a docking group, well, it has a small preference for going C-terminal. And it's only when we have the docking groove and an RRM that's flanking that RS domain, that we actually get this strong preference for going for the C-terminal end of RS1. So just to summarize some of this, I tried to put it in terms of free energy a bit. And what we have here is we're comparing the fully functional kinase substrate where we have SRPK here. It has a viable docking site in the MAP kinase insert area, and it also has the RRM2, which is, we've shown to be essential, and it's also in our structure. And that kinase, if you look at the free energy for initiation, it wants to go into the center of the RS domain, right, by the initiation box. Doesn't want to go into RS2. But preferred and doesn't want to go towards the N-terminal end of RS1. It wants to stay in this well here. Okay? You can take out all of those contacts that I was talking about. So you've got basically a stripped down SRPK with an RS domain, no docking group, no RRMs. That one end of the free energy curve is very flattened out. So that now, while it has a small preference for going N-terminal, it doesn't have any strong preference for any part of the RS1 segment too much. It's only when we put in like the docking group or one of the RRMs that we begin now to push up one end of that profile. And still it can go towards the N-terminus, but it gets harder and harder. It's only until we put both of those elements in that we get this strong preference for going into the center. Now, why is it still wanting to go into that center? We've isolated the elements that are important for this. But the interesting thing is that we know it starts here, but we can knock those residues out and they'll just go down here. And that might have to do with this, this melting of the beta strand that Gloria was talking about. We know that we can make the RS domain larger, and this could probably move out. But it still doesn't explain why we're going towards the center. And those are some features that we still have to work out as well. Some other questions is, when we're talking here about initiation and the factors that are important in making this kinase initiate what it does, we map that out. But why does this kinase have an intrinsic, or does it have an intrinsic preference for moving in one direction, one residue to the other, and that we still have to answer. My feeling is it might have something to do with the fact that a lot of these kinases are the same, that they have these channels, and in this case we have a channel that's highly electronegative, and it might not just accommodate phosphates, so it can't move in the opposite direction, and so it's constrained. There's all this negative charge here, so it has to expel the phosphates that way. That could be a source for this directionality. But quite clear, it is this docking group and also this RRM that appears to be very important in establishing where this thing starts. So I'll stop and just acknowledge people that worked. Chen-Ting Ma did a lot of developed all of this cleavage constructs and this methodology for looking at the directionality of these kinases. John's done a lot of work on binding, and Adolfo's done a lot of the mass spec work. Brandon got this whole thing started. And we really would not get what we get accomplished if it wasn't for the excellent collaborators we have. Lori with the structural work and Fu with the biological work. We've actually working quite well as a team together in trying to answer all of these questions. And finally, language. Questions for Joe?
Yes. Is there any possibility that there are docking sites for the phosphorylated serines to help the product move in one direction in addition to...
I glossed over that. Lori talked about that this morning. There's actually
Because of an artifact of the crystallization, we used areas like A and P and P, and it had a very small amount of ATP on it, and it primed the first site. And while we can't see the intervening sequence here, we do see a little phosphoserine here in this electropositive pocket that appears to be a docking site for phosphoserine that would be coming from the substrate. Now we've mutated out all the residues there, and we still have a directional kinase that wants to go in the center. So this doesn't appear to be important in that directional mechanism, but what we did find was that it slowed down the rate of which later phosphates, later serines get phosphorylated. So it might be doing something later on in the reaction, not in the beginning. But there is a docking site for that.
So the rate is, the phosphorylation rate is rather slow. It's obviously not going to be regiospecific kinetics, right? Because the substrate is not have an equilibrium like you normally expect in a product, substrate, product relationship, right? So my question is the rate of phosphorylation determined by the rate the substrate is processing through the catalytic side?
That's a great question. We don't know the answer what exactly it is, but I don't know if it's a translocation of any sort or whether the actual translocation is slow. It's of the order of several percent. We consider that slow. I would consider that slow by pKa standards, but there are other kinases that are slow with their substrates, so I don't have a feeling for what's slow or fast.
Well, considering the substrate is already balanced, that seems real slow.
Yeah. I mean, it's definitely under the level of the pKa. There's no question. I don't know why that's so. My personal feeling is that because there's so many contacts and they're so high activity, there might be a translocation issue, or at least of some sort. I just don't know what that is.
Don't forget you have to get a new ATP on there every time.
You have to
Presumably that's fast, right? Because other kinases can do that.
I'm not. Have you measured that, Jeff?
We haven't actually measured how fast the ATP gets down. It's a really interesting question. It would be very useful to get a V over K for it. I would presume that it's probably going to be your typical Km, in which case there shouldn't be any barrier for the binding of that.
Except that your substrate is there.
Well, there's a lot of kinases do this all the time. They have a buried pocket for ATP, and the substrate is right on top of them, yet they're random.
Yeah, I know.
It's a mystery.
Yeah.
But
this is a case where you might be able to get to the bottom of that.
We'll measure K.
Do you have to, I don't know if anybody's done single molecule things, but it seems like if you had a fluorescent probe on the small lobe, you could actually follow a set of motions in going through that processive event.
Oh yeah, that's exactly what we're interested in doing. I got to talk to you about this. No, that's a great idea. I mean, I actually look at this kinase substrate system in a way it's kind of like a machine.
Yeah.
Where you're using phosphates to move something. I've never thought of kinases in that sense. I saw them as hitting this guy, these ships passing in the night. That's it. But this is a kinase that has a relationship with the substrate and moves it. So it's kind of like a machine. And I think it was very unique to this molecule.
I mean, I guess the bit about the substrate not coming off is doesn't necessarily mean it doesn't kind of partially come off. It just means you can't trap it. Right?
Exactly.
So,
yeah, and I can rule out the possibility that it's in some sort of a hydration shell around the, you know what I mean, so that the competitor can't come in when it's in that shell and take it out. I can't rule that. Or whether there's some other possibility in these other contacts here that part of it doesn't pop out, where the other is attached.
So I was actually wondering how much I didn't quite understand the crystal structure. Is there a serine in the active site?
No. There's a phosphoserine that's in a pocket right. Glory can probably discuss this better. That's to the right of the active site, and it's presumed that that's coming from the substrate that's partially phosphorylated. So the idea is that might be driving the reaction in one direction, although the mutational data is not entirely consistent with that. But, yeah.
One last question.
I'm sure you did this and you're not talking about it because it didn't work, but can you go in and replace some of the serines with acids or glues and take this thing out without having to skip steps and do stuff like that? Or give it one at the beginning so that it wants to go process it or something?
One of the first things we wanted to address was this issue of the rigidity of the starch, right? And what we did, we didn't put in the glues, but we put in strings of alanines. We took out 4 out in a row because we didn't know where it initiated, so we just wanted to blanket it. And it just moved over and did the other ones. It has that flexibility engineered into it so that it just moves. If the regio-specificity looks the same, it's quite a mystery that, and my gut tells me it has something to do with that R2, pinning that thing down and keeping it in an arrangement like that. So, but yeah, we have done that. We haven't done the glutamate, so that would be interesting to do though.
Okay, our next